Yes.
Interest is in place.
Yeah.
That's you can do people can join.
Yeah. Hey, Chris, we just had a coffee break, so maybe we can wait like a couple of minutes. Would that be okay?
Yeah, no problem. Like 5-10 minutes. Okay. Sounds good.
Thanks.
Chris, see how his life is.
Hey, Chris.
Hey, how's it going?
Good. How are you?
Oh, all right. Yeah, how are you? How are you liking being a professor? How's your first year?
Survived. So far, so good.
So far, so good. Good. I'm glad to hear. Yeah. Yeah, I'm sorry I couldn't make it to the workshop in person. I'm just yeah, I really wanted to go, but yeah, I don't know. I told you Shang this, but yeah, my wife is pregnant and she's gonna like do in the next like week,
Congrats.
in the next week or so. So it felt like it's probably a bad idea to go. Yeah.
Yeah, congrats to you both.
Thank you. Yeah.
Yeah, we should catch up. I'll follow up with an email and then we can have a Zoom call or something. But
yeah,
depending on your availability.
Yeah. I mean, next week should both be fine for me. Hopefully, we'll see. I mean, well, I don't know. Well, I don't know. Should be okay, but you never know. I don't know. There's a lot of
Meta is treating you.
That's okay. Yeah, it's cool. It's good. There's I will give kind of a summary of like the research that we've been doing this year and that I've been doing this year. I guess not all of us in this talk, so we'll see.
Cool. Thank you. Looking forward to it. Yeah.
So, okay, welcome back. It's my great pleasure to introduce our second invited speaker, Chris Paxton. Chris is a robotic research scientist at FAIR Labs at Meta. His research is along the around the basically kind of allowing robots to work alongside humans to perform complex and multi-step tasks using a combination of learning and planning. So he got a PhD in computer science from Johns Hopkins. He used to work at NVIDIA Robotics Lab, and now he's working at FAIR at Meta. So Chris, it's all yours.
Thank you. Yeah, I'm glad to be here. So yeah, today I'm going to talk about some research that we've been doing over the last year. So this is basically how we can get towards building robots that work in people's homes and that can work alongside us, in particular with a focus on generalization to unseen environments and unstructured scenes. So really what we want is robots that can help people out with everyday tasks, like putting things away, moving objects around, like cleaning up, whatever you might want. Just like something that'll help you. So in your home. This is what current home robots look like. This is Amazon's Astro. It can in fact do quite a lot of these things, like moving around in your house, but it clearly has no arms. It's not super useful in any way. It's certainly not worth the price, but it's a great little robot actually. But so what we really want to move towards is something like that to something like this guy. This is a low-cost mobile robot that we have moving around in a wide variety of different environments, doing things like pick and place and manipulation of various objects, putting things in drawers, and cleaning up, whatever. So how can we build this? So to be able to make a robot like this useful, we would want it to be easy to talk to, so easy to control, which we say that we want to be able to do this with natural language expressions, if at all possible. It should be able to understand the world around it. It needs to be able to perform complex multi-step tasks based on sensor measurements alone. So it doesn't have like privileged information like you see in a simulator, right? It actually has to be able to perceive the world And the world is not easy to perceive in this case because there could be objects all over the place. And it should have a wide range of manipulation capabilities. So in particular, we see that the world is full of all kinds of different ways that you need the world. It also needs a lot of semantic knowledge about how the world is arranged, because there's a lot of objects like this that can appear in any different configuration all over the place. And so it needs to be able to understand how to actually accomplish all of these tasks. So the current kinds of systems that we have before are systems like this one. This is a task and motion planning system. So it is relying on object detectors for each of these individual objects. But the nice thing about it is that it can perform these complex long horizon tasks. Like in this case, it's miming sort of making soup, where it has to like pour some stuff into a bowl and turn a knob and activate it to turn on this oven. The problem with these kinds of things is that they generally require quite a lot of work as far as setting up like all of the different problem definitions, motion planners, samplers for where objects can be grasped and placed, and all of that has to come from somewhere. And what it means in practice is that you usually have to you have to teach it all this, and that requires a lot of engineering. So to address this, we want to move towards like figuring out how we can plan sequences, generate sequences of actions that satisfy task constraints, arranging objects, stacking them, putting them away, whatever it is. We need to be able to understand the scene that a robot is in, so it can move around, answer questions, whatever. It should be able to. It needs some kind of motor skills that allow it to actually robustly interact with that world. And finally, we need to know how do we know whether or not we have one of a system like this. So I'll also talk a little bit about benchmarking and deciding and building and sharing and scaling home robots in the future. So we have both simulated and real world environments, and we want to be able to make sure that we can run stuff in simulation and in the real world. So I'll talk a little bit about benchmarking and bringing all this stuff together at the end. So I'm going to go through this. This is going to cover a few different papers. So if anyone has any questions, please don't hesitate to like ask or something. I might need help catching them, but I'm not sure how the system works here. So yeah. So to start with, let's talk about those complex. Let's go back to those complex structures I was mentioning earlier. So there's a lot of previous work. There's a lot of work on like having robots do like object rearrangement or understanding complex scenes. A lot of it, when it comes to actual robots, is limited to sort of tabletop scenes with known objects. But we do know that there are these models like large language models, GPT, PaLM, and so on, that can perform complex multi-step inference. Where they have some amount of the problem is described as tokens, as some context that gives you some information about what the world looks like. So with robots, we want to figure out what that might look like. What exactly is the context, so we can build like a GPT equivalent for a robot so that it can do anything we want to, right? So the first option might be that we have something like image patches, object level reasoning, where we detect all the things that might be relevant to the robot and then throw them into some large transformer, or we do something fully implicit where we don't have any particular structure provided. So what I'm going to say is that, at least to start with, we want to go with object level reasoning will give us this foundation for building multimodal LLMs that allow our robots to do this multi-step rearrangement task. So in the past, so we've seen that you can combine end-to-end learned policies to be able to perform these kinds of tasks, but you still have to do a lot of the engineering for features and predicates and so on, even if you're training in simulation. So instead, let's say that instead of predicting like motor torques or where to move the robot, let's say that we want to predict purely in visual space. That way we have a nice generalizable policy which tells us how the world should change. We're going to predict basically at the high level where the points that we see should move and how the scene should change. And this will give us like a fundamental piece that allows us to do object rearrangement and planning. And as well as later on, I'll tell you how it goes into actions as well and motion. Right. So what we see is that so for example, if I tell the robot something like move the red mug in front of the blue pitcher, it tells me that these pixels that correspond to that it's seen from the mug should move there. And we see the same thing, like moving a bottle of mustard, it'll go up on top of this object, or moving a pitcher to the left of this mustard, and so on, right? So this is nice in general because it's all operating in this vision space, and we can train policies like this, and see that they do in fact scale to even just to very different scene geometry and totally unseen objects fairly well, at least for just picking and placing one individual object, right? Okay, so starting from this, we want to say we want to extend this to multi-step tasks. So in particular, given a partial viewpoint cloud and language description of a goal, let's find a sequence of actions to take that accomplish that goal. right? Where an action is basically just like move this set of points to that location, right? So we can start by generating this data in simulation. So we generate a really large data set in simulation of objects of different structures and different objects being placed and moved around associated with templated language. The nice thing about this simulation lets us quickly generate tens of thousands or hundreds of thousands of different scenes. So in the end, we get about 100,000 different arrangements of objects based on 3D meshes, just simulating them in Bullet, running them through rendering, randomizing color, texture, etc. And then we can train our multimodal transformer, which is autoregressive, to be able to predict just like where the next object should go in order to accomplish these tasks, right? So, and based on that, just like the very simplest version of this, where you just take in a bunch of different object point clouds and you can train on all this data, we can see that it's able to actually transfer to a real robot nicely for doing things like putting these objects into a circle or a line, or it can determine which objects it should move versus which ones it shouldn't. And again, the nice thing about all these is that while you may recognize some of these objects as being from like the YCB, like very well-known object data sets, none of them appear in the training data. So this is actually generalizing. And finally, just an example of it, dealing with boxes, which have to be oriented properly and placed in a line. So now we have these pieces allow us to do like fairly precise placement, rearrangement, large on large numbers of objects. But it still couldn't, like that first version of this, that just this autoregressive transformer isn't able to actually like build a tower or anything like that. So it doesn't have any understanding of stability or what poses will work. So why this is hard is because there's actually like a lot of very small cases where you see things failing. To be able to make them reliable, you need to be able to handle stuff like this. And so in this case, like for example, on the far right here, you see from the point clouds that the robot has seen, it really can't tell that, for example, that cup is like just barely on top of this knife. So it will actually fail. Like it's not a good placement. But just like millimeters over would be fine, right? So this does actually require a good amount of precision to get this right. So we go to diffusion models as another option for handling this. So in this case, diffusion models are they're very popular now for image generation. They let us create complex structures that we can see in the real world that are able to like all of these images here are generated from diffusion models. They're able to build these complex structures in image space, but they're not able to define what will be physically valid. And we also don't have a good way of mapping them to 3D actions. And so there is some work out there on 2D actions, stuff like this, which I can get to. But so let's model that structure creation problem as a diffusion problem. So where we take objects and we do put them through a reverse diffusion process to be able to figure out where these things should go. So the way that we set this up is that you can repeatedly sample object poses and refine them via this diffusion model, and to be able to get like a nice distribution of samples, choose the best one using a trained discriminator, and now you have this nice approach which will actually scale to any objects and be able to build various complex structures. So we tested it on this large set of previously unseen objects, textured objects from a bunch of different sources. They are where we see that the old autoregressive version of this, which just have a transformer predict where each object should go, does fairly poorly. Adding in the diffusion process makes things quite a bit better. And that means that you can get really nice results for things like stacking and object rearrangement, where it can reliably place them on all kinds of different situations. And of course, these are all on sensor data with real point clouds. It's able to predict how the object should move around. And then and also we can, of course, test it out on real robots and have it rearrange these things in the real world, and for things like stacking and placing. So what we have here then is that we have a nice approach which allows us to do things like figure out, at least at a high level, where objects should move to satisfy language expressions. It's fairly precise and reliable. It does a good job at making these kinds of predictions. We need like low-level skills and so on to combine them, right? I will take one aside, which is this is a paper that we just presented at IROS, which is like, I do think when we talk about moving to more types of structures, one thing that is worth exploring is GPT. Like it allows us we are able to use to predict object relationships using large language models like GPT or Llama to be able to figure out how objects should be arranged. Tying that into perception and all is still future work, but I think it's a really exciting direction. So so now our robot needs to get to these locations, and we need to be able to manipulate objects. So how do we represent a whole scene? So beforehand, I talked about how we should have about how we're doing object level reasoning. So now one problem is that if I'm navigating around in a scene, it's not totally clear that that object level reasoning is quite right yet, because I don't know which objects I care about, first of all, especially if I want to go to a particular location. Like if I say something like, go to the kitchen or get me something to drink, I'm not sure that I have like the right objects in my context yet. So for this one, maybe we start off by building some semantic map that we can then use later on to create get the objects that we need. So this is some work that we presented at RSS, which is clip fields. So we start out with, we build like this implicit NERF-like representation of a scene where we learn to basically train a function, which will be able to, which has a bunch of different heads, which will give us things like clip features associated with different spatial locations. So this is what we think of as like a NERF-like implicit representation, which means that we actually do kind of train it on like the data from this particular scene. It takes a little bit, and then you get a nice representation, which you can then use downstream for various types of queries. So for example, one of those queries might be warm up my lunch, where we see that basically it can highlight the particular location where this microwave is in this mini kitchen, so that the robot can move over there and then it can do stuff with it, right? And so in practice, you can then plug this in on a robot and ask the robot things like, and choose different locations in this 3D semantic representation the robot's built as the robot explores, and then it can go to these different locations. Like for example, if I tell it to wash the dishes, it can go over to, and it'll head over to a location for that, for example. So there's a dishwasher there, and that's what and the robot is looking at the dishwasher correctly. So that's great. So this is very simple, but it's still not tied into motion planning. It's not really capturing geometry. We actually are just using the original point cloud and querying over it. So let's learn an extra head which captures scene geometry and affordances. So there was some prior work called ISDF, which learned the sign distance field in the same kind of implicit representation and used it for planning. Also at IROS this year, we proposed this approach called USA Nets, which is semantic and affordance networks, which lets us do things like, so basically in addition to the basic clip fields components like predicting language, so like having a language output head will also predict this distance field function, which lets us do things like say, okay, so there are jackets hanging in a closet. Now we can plan a path over there that avoids collision with all the geometry, gets to that location and goes. So the general approach is this. So basically, given a language expression and the world representation, all of that information goes into the planner, which generates a trajectory, and then we can send that through, and then we can score that trajectory based on basically how close it gets to the target location and whether or not it satisfies this language expression, like getting to that jacket. And so then you can deploy it on a robot. You can have it do things like look at vent and drive around in this very cluttered room, and it's able to understand all these objects without explicitly labeling where they are, or explicitly detecting the set of objects that we care about. So this is nice. So now we can navigate to different locations. Now we have once we get there, we can generate our high level action plan as to where every object should go. But during that one, we still don't know how to actually manipulate things when we get there. So finally, now that we have these two things, let's talk about learning low level skills. And then finally, I'll go on to kind of the benchmarking part. So this is work. These two papers are at Coral, by the way. So I'm going to talk about two different things here. And so first of all, the core idea is that as with both of these other things, we're going to learn spatially abstracted skills, right? So I want to pick a place or area in the world to act, and then apply some kind of motion parameterization from that, right? So in one case, we might be like picking an object to moving an object from place to place, opening a drawer, whatever it is. A lot of things can be expressed in this way, and that is in fact the same kind of representation that we're using at a high level, and for navigation and for like high level planning, like how to rearrange scenes, right? So this is the nice thing about this is that it's very general, right? And so what we mean by that, for example, is that this is work that'll be presented by Wenxuan Zhou this week, and with Dave Held, who I think may have given a talk this morning already. So basically we train so in this case, we can train two different components. We can train this policy via RL, with the goal being to rearrange objects into different configurations using non-prehensile manipulation. The nice thing about this is that we can predict where to make contact and which motions to make, and then you're able to push objects around in the scene in order to, and we'll get to some examples of this. So for example, if I want to like flip this object upright, I send that position to the object, and then we are able to just kind of like touch it, move it around. The robot learns all of this in simulation, and all of this importantly is being applied on objects that we haven't seen before. So it's really able to do really dexterous manipulation of these unseen objects. And another example with this same YCB mug that I've showed a bunch of videos of already, where it's able to move this thing around, and you can see it placing it in the correct positions in just a minute. So we can also apply this to language conditioned policy learning, where we have the same type of division. We predict an interaction point or region, and then predict a trajectory from that point. And so in this case, this is work called SLAP, which is spatial language attention policies, which we worked on. This is work from Meta, and in this point, this kind of representation, we're able to do a bunch of different tasks. We tried on two different robots, the Stretch and the Franca arm. It's able to do things like closing drawers, picking up lemons from basket, picking up pears, whatever. So we require relatively little data to learn these policies, which means that it's very fast to train and very fast to deploy. And so we can do things, and of course, it is also very precise, importantly. So it's able to do things like picking up this lemon, which is a very small object, right? And very hard to grab successfully because it's a hard plastic toy where it'll slip. And so we also showed on these mobile Stretch robots, where we can have it do things like move over to a drawer, open the drawer, pick stuff up out of the drawer, and so on. And so the robots are grabbing things off of shelves, etc., pouring things out of the cup, whatever. So yeah, so this is what's nice about this is that we now have the different pieces to be able to execute these longer horizon policies on this robot. We have some idea of what kinds of representations we can use for navigation and long-term planning. But what we really need to do next, and with the last few minutes, I'm going to talk about how we can bring all this together, and how we can benchmark it and show that we actually see whether or not we actually have these kinds of things. So this is the most recent project that we've been doing, which is Home Robot, also going to be presented at Coral by Sriram Yanamandra on Thursday, I think. So the problem is, so basically, let's start with the simplest version of this problem, which is basically, I want to be able to pick up anything from anywhere in any environment and move it to any other location. So it's just one step, or two steps really, like pick and then place. But it's a hard two steps because I don't know what the objects are, and the scene and the environment is very large, right? So in the top, you can see a real world instantiation of this task, where it's got to go over to a chair, find a toy animal, and then move it to a table. On the bottom, you can see it moving a pitcher. So we have to get in the past, I think there's been a lot of benchmarking effort in habitat and simulation environments on geometric rearrangement. So where you have to move an object from one location to another. So, but these are given as actual like poses, right? Locations in the world, which we may not really have access to. So instead, we want to pick up the object from the table and move it to the sofa. So we're swapping it out for language, right? And in particular, we care about three words in this expression. We care about the object name that we want to move, the start receptacle, which is kind of a hint that says like I should look for objects like this somewhere in my environment and I should put them somewhere else, and the goal receptacle. And then in the past, we've seen that these there's a lot of different work on benchmarking and on real world benchmarking. So uniquely, ours has like open licensing, continuous action, sim to real. It also comes with a full robotic stack, which is used for a lot of the experiments that I've shown you so far, or some, and so we can do this both in simulation and in the real world. We generate 60 environments in simulation, 150 objects, 8,000 instances in particular. So it's a very diverse data set. In particular, these objects are curated to be relatively small, graspable, realistic objects. You're not going to see like an elephant in the kitchen or something like that. Like there's going to be, well, unless it's a toy, right? But in particular, this makes it quite a bit harder than a lot of object search benchmarks, because you see that things are actually quite small and hard to find. So the way that it works is that on the benchmark, you get a point for every time for finding the object, picking it, placing it. putting it on a goal and how long it takes, and then we're going to compare, and then you compare how long it takes as well if you need a tiebreaker from that point. To begin with, you run everything in simulation. So these are scenes from the Habitat Synthetic Scenes data set, which is this large data set of many different object scenes. The nice thing about them is that all of these scenes are fairly realistic. They're authored by humans. They look like human environments in that they are cluttered and there's lots of distractors and things like that. So you can see some images here. It actually does make it very hard for a mobile robot to move around in. We use a bunch of different object data sets that are also open licensed that we can use for learning here. And bring it together. You have these robots which have to explore in these complex multi-room environments and do grasping and placing, right? So, for example, in this case, they're exploring to find different objects in these in these different homes. This guy's not moving, right? But just to give a picture of what these look like and what the kind of problem is that we want to solve, right? And so here, so it's picked something up and now it has to move around and find the correct type of receptacle to place it on. I will note that any receptacle is fine for the goal, so it's a fairly easy version of this open vocabulary manipulation problem, right? Where you don't know the environment, but like there's a lot of different possible solutions. So for example, on the far left, it didn't need to move very far to place the pillow down on a table, right? So to start out with, we start out with just like basic off-the-shelf policies. So none of the stuff that I actually talked about in the first half of the talk are all policies trained using segmentation models or just basic motion planners to find objects and explore. This is nice because we see we're able to test these things out. We test them out both in simulation and in the real world. You can see the robots, the agents exploring here, and we do rely on this data, basically open vocabulary object detection for now. Yeah, but then we can then test these things in the real world, these are two success videos. These are tested in an apartment that Facebook has in California. So we're able to go and pick up objects, move them around, run like large sets of experiments on them, and we also have control over it. So we control the lighting, we can control the furniture, etc. So it's not like we're running these in Airbnbs or in a lab environment. And that means that we can do a real world benchmark and we can actually compare our progress on this. And so, sorry, the next step. So we released all of this code together as this sort of home robot library, which has motion planning, manipulation. It has like the policy learning from SLAP, like I mentioned earlier. It has grasping, etc. So you can try all this stuff out in any environment. We've tested it in quite a lot of environments. The other thing that I should mention is that we are actually running currently a competition, which is just the web submission's closed, but this is a competition on this benchmark. The top 3 entrants, which we're going to announce soon, are going to be tested in our lab environment. And so hopefully we'll be able to run this. We'll run this competition again, but I'm pretty excited because it is in fact like a really realistic problem statement for robots in homes. And I think that we can use this to make a lot of real progress. So just to conclude, from a technical side, I think that these kind of spatially grounded representations work for long horizon planning, navigation, manipulation. There are ways that we can train them, and so they generalize really well to long horizon tasks and unseen environments, unseen objects. So that means that we're really making a lot of progress, I think, towards building like general purpose robots that work in homes. That being said, and most recently, we've been looking at how we can benchmark these things. A lot of that, there's both code, simulation, and our NeurIPS challenge, all available online. Take a look at it. Otherwise, I think thank you to everyone who has been involved in this and my research. And otherwise, yeah, let me know if you have any questions. Thanks.
We may have 2 or 3 questions from you. Any questions? Chris, I have one question. So when you talk about the clip field, you also mentioned that you use the scientist function to give some spatial information, right?
Yeah.
Could you briefly explain why you chose a scientist function, learning scientist function, maybe instead of using other representation like NeRF, neural latency fields?
So we actually do use it's not radiance fields, but we do actually learn an implicit function, right? So this is you could think of it as being very similar to a NeRF, right? The point is that one of the outputs of the NeRF has to be this distance field, right? That tells us how far from the structure we are for this. Yeah, this is no like radiance component here, right?
Let's see. Thank you. Any other questions?
Thanks, Chris. This is you. I have one question about home robots. So my student is trying to use it, and we found out you don't have ROS supports for the home robot package, or you add some ROS support to it.
Yeah, we do have ROS support for it.
You have?
Yeah, this is all based on ROS. Not in simulation. We don't use simulation. We don't like the simulation environment it's not ROS. It's ROS agnostic, I would say. Yeah, that's it. So the real world environments the real world wrapper is all based on ROS. Everything is ROS compatible. Yeah. So do you mean like, is there a ROS version in simulation specifically?
Yes, because you will train the policy or run the evaluate like the testing in simulation first, right?
Yeah. That's a good point that not many people have asked for that, because I think like, so for the RL kind of training, like you can't really use ROS effectively, but honestly, that's a good thing to add. So yeah, let's take that offline. I think we can talk about it. I would be happy to add that. Yeah.
Thanks. Okay, thank you. Thanks, Phil, again.
Yeah.
I had one other question about home robot.
Sure.
So yeah, I'm curious in the baseline and then in the submissions that have been coming in, do you know what the big bottleneck is? Is it grasping? Is it finding the objects, navigating?
It's perception for the most part. It's like, I think navigating is relatively well understood. I would say like efficient exploration is hard. I think that's a big problem in the real world, or in particular when perception gets noisy, because you have to integrate predictions over time and be able to make good decisions. I think that, yeah, I think it's basically like the real biggest bottleneck is perception. So in our case, what you see is that when we do experiments in the paper which compare ground truth segmentation, and you should check out the actual poster session, right? But they talk to the student. But there's a huge difference between ground truth perception and and using like off-the-shelf perception models like DEDIC, right? So we're like just order of magnitude of difference in performance. So I would say that's the biggest thing to start with. But I don't think that, importantly, I don't think that's a perception problem, like a computer vision only problem. The real problem is you have to be able to aggregate detection information over time, which means that really we just shouldn't be learning. We shouldn't be leaning on these open vocabulary detection models. We should be training robot policies that can do this. And that is going to require, I think that is still going to require a lot of offline data, because one of the hard aspects of this is that there are half of the object classes that you care about during the test and validation sets are not seen in training data at all. So, and that's one of the things that I think makes it a more realistic benchmark, but it does make it much harder, right?
Got it. Thank you.
Mm-hmm.
Okay, thanks, Chris. We're going to move to the next speaker.
Okay, thanks.